brain neuron view of a convolutional layer, similar to what we looked at for the neurons in the last lecture. So what we have is that at every spatial location, we take a dot product between a filter and a specific part of the image, right? And we get one number out from here. And so this is the same idea of doing these types of dot products, right? Taking your input, weighting it by these W's, right? Values of your filter, these weights that are the synapses, and getting a value out. But the main difference here is just that now your neuron has local connectivity. So instead of being connected to the entire input, it's just looking at a local region spatially of your image. And so this looks at a local region, and then now you're going to get kind of this how much this neuron is being triggered at every spatial location in your image, right? So now you preserve this spatial structure, and you can say, be able to reason on top of these kinds of activation maps in later layers. And just a little bit of terminology. Again, for we have this 5x5 filter. We can also call this a 5x5 receptive field for the neuron, because this is the receptive field is basically the input field that this field of vision that this neuron is receiving, right? And so so that's just another common term that you'll hear for this. And then again, remember, each of these 5x5 filters, we're sliding them over to the spatial locations, but they're the same set of weights. They share the same parameters. Okay, and so as we talked about, like what we're going to get at this output is going to be this volume, right? Where spatially we have, let's say 20 by 28, and then our number of filters is the depth. And so, for example, with 5 filters, what we're going to get out is this 3D grid that's 28 by 28 by 5. And so, if you look at the filters across in one spatial location of the activation volume and going through depth, these 5 neurons, all of these neurons. Basically, the way you can interpret this is they're all looking at the same region in the input volume, but they're just looking for different things, right? So they're different filters applied to the same spatial location in the image. And so just a reminder again, to, kind of comparing with the fully connected layer that we talked about earlier. In that case, right, if we look at each of the neurons in our activation or output, each of the neurons was connected to the entire stretched out input. So it looked at the entire full input volume compared to now where each one just looks at this local spatial region. Question? Okay, so the question is, within a given layer, are the filters completely symmetric? So what do you mean by symmetric exactly, I guess? Right, so the filters, are the filters doing the same dimension, the same calculation? Yes. Okay, so is there anything different other than they have the same parameter values? No, so you're exactly right? We're just taking a filter with a given set of 5 by 5 by 3 parameter values, and we just slide this in exactly the same way over the entire input volume to get an activation map. Okay, so we've gone into a lot of detail on what these convolutional layers look like, and so now I'm just going to go briefly through the other layers that we have that form this entire convolutional network, right? So remember again, we have convolutional layers interspersed with pooling layers once in a while, as well as these nonlinearities. Okay, so what the pooling layers do is that they make the representations smaller and more manageable, right? So we talked about this earlier with someone asked the question of why we would want to make the representation smaller. And so this is again to have fewer, it affects the number of parameters that you have at the end, as well as basically does some invariance over a given region. And so what the pooling layer does is it does exactly just downsamples, and it takes your input volume, so for example, 224 by 224 by 64, and spatially downsamples this. So in the end, you'll get out 112 by 112. And it's important to note this doesn't do anything in the depth, right? We're only pooling spatially. So the number of your input depth is going to be the same as your output depth. And so, for example, a common way to do this is max pooling. So in this case, our pooling layer also has a filter size, and this filter size is going to be the region at which we pool over, right? So in this case, if we have 2x2 filters, we're going to slide this, and so here we also have stride 2 in this case. So we're going to take this filter and we're going to slide it along our input volume in exactly the same way as we did for convolution. But here, instead of doing these dot products, we just take the maximum value of the input volume in that region, right? So here, if we look at the red values, the value of that will be 6 is the largest. If we look at the greens, it's going to give an 8, and then we have a 3 and a 4. Yes, question? Yeah, so the question is it typical to set up the stride so that there isn't an overlap? And yeah, so for the pooling layers, it is, I think the more common thing to do is to have them not have any overlap. And I guess the way you can think about this is, basically we just want to downsample. And so it makes sense to kind of look at this region and just get one value to represent this region, and then just look at the next region and so on. Yeah, question? So the question is, why is max pooling better than just taking doing something like average pooling? Yes, that's a good point. Like, average pooling is also something that you can do. And the intuition behind why max pooling is commonly used is that you can have this interpretation of, if these are activations of my neurons, right? And so each value is kind of how much this neuron fired in this location, how much this filter fired in this location. And so you can think of max pooling as saying, giving a signal of how much did this filter fire at any location in this image, right? And if we're thinking about detecting, doing recognition, this might make some intuitive sense where you're saying, well, whether a light or whether some aspect of your image that you're looking for, whether it happens anywhere in this region, we want to fire at with a high value. Questions? So the question is, since pooling and stride both have the same effect of downsampling, can you just use stride instead of pooling and so on? Yeah, and so in practice, like I think looking at more recent neural network architectures, people have begun to use stride more in order to do the downsampling instead of just pooling. And I think this gets into things like, also like fractional strides and things that you can do. But in practice, this in a sense, maybe has been a little bit better way to get better results using that. So yeah, so I think using stride is definitely, you can do it, and people are doing it. Okay, so let's see, where were we? Okay, so yeah, so with these pooling layers, so again, there's some design choices that you make. You take this input volume of W by H by D, and then you're going to set your hyperparameters for design choices of your filter size, right, the spatial extent over which you're pooling, as well as your stride. And then you can again compute your output volume using the same equation that you used earlier for convolution. It still applies here, right? So we still have our W total extent minus filter size divided by stride plus 1. Okay, and so just one other thing to note, it's also, typically people don't really use zero padding for the pooling layers because you're just trying to do a direct downsampling, right? So there isn't this problem of like applying a filter at the corner and having some part of the filter go off your input volume. And so for pooling, we don't usually have to worry about this, and we just, directly downsample. And so some common settings for the pooling layer is the filter size of 2x2 or 3x3, strides 2x2. You can have also, you can still have pooling of 2 by 2, even with a filter size of 3 by 3. I think someone asked that earlier, but in practice, it's pretty common just to have, 2 by 2. Okay, so now we've talked about these convolutional layers. The ReLU layers were the same as what we had before with the just the base neural network that we talked about last lecture. So we intersperse these, and then we have a pooling layer every once in a while when we feel like downsampling, right? And then the last thing is that at the end we want to have a fully connected layer, and so this will be just exactly the same as the fully connected layers that you've seen before. So in this case now what we do is we take the convolutional network output. At the last layer we have some volume, so we're going to have width by height by some depth. And we just take all of these and we essentially just stretch these out, right? And so now we're going to get the same kind of, basically 1D input that we're used to for a vanilla neural network. And then we're going to apply this fully connected layer on top. So now we're going to have connections to every one of these convolutional map outputs. And so what you can think of this is basically now instead of preserving, before we were preserving spatial structure, right? And so, but at the last layer at the end, we want to aggregate all of this together. And we want to reason basically on top of all of this as we had before. And so what you get from that is just our, score outputs as we had earlier. Okay. Okay, so the question is, what are the 16 pixels that are on the far right? Do you mean the... each column. The green ones or the black ones? The one with, hold on, pool. Oh, okay. Yeah, so the question is, how do we interpret this column, right, for example, at pool? And so what we're showing here is each of these columns is the output activation maps, right? The output from one of these layers. And so starting from the beginning, we have our car. After the convolutional layer, we now have these activation maps of each of the filters slid over spatially over the input image. Then we pass that through a ReLU, so you can see the values coming out from there, and then going all the way over. And so what you get for the pooling layer is that it's really just taking the output of the ReLU layer that came just before it, and then it's pooling it. So it's going to downsample it, right? And then it's going to take the max value in each filter location. And so now if you look at this pool layer output, like for example, the last one that you were mentioning, it looks the same as this ReLU output, except that it's downsampled, and that it has this kind of max value at every spatial location. And so that's the minor difference that you'll see between those two. So the question is now, like, this looks like just a very small amount of information, right? So how can it know to classify from here? And so the way that you should think about this is that each of these values inside one of these pool outputs is actually, it's the accumulation of all the processing that you've done throughout this entire network, right? So it's at the very top of your hierarchy. And so each actually represents kind of a higher level concept. So we saw before, for example, Hubel and Weasel, and building up these hierarchical filters, where at the bottom level, we're looking for edges, right? Or things like very simple structures like edges. And so after your convolutional layer, the outputs that you see here in this first column is basically how much do specific, for example, edges fire at different locations in the image. But then as you go through, you're going to get more complex, it's looking for more complex things, right? And so the next convolutional layer is going to fire at how much, let's say certain kinds of corners show up in the image, right? Because it's reasoning, its input is not the original image, its input is the output, it's already, the edge maps, right? So it's reasoning on top of edge maps. And so that allows it to get detect more complex things. And so by the time you get all the way up to this last pooling layer, each value is representing how much a relatively complex, sort of template is firing. right? And so because of that, now you can just have a fully connected layer. You're just aggregating all of this information together to get, you know, a score for your class. So each of these values is how much a pretty complicated, complex concept is firing. Question. So the question is, when do you know you've done enough pooling to do the classification? And the answer is you just try and see. So in practice, you know, these are all design choices, and you know, you can think about this a little bit intuitively, right? Like you want to pool, but if you pool, you know, too much, you're going to have very few values like representing your entire image, and so on. So it's just kind of a trade-off, something reasonable versus people have tried a lot of different configurations. So you'll probably cross-validate, right, and try over different pooling sizes, different filter sizes, different number of layers, and see what works best for your problem. Because yeah, like every problem with different data is going to, you know, different set of these sorts of hyperparameters might work best. Okay, so last thing, just wanted to point you guys to this demo of training a CommNet, which was created by Andrej Karpathy, the originator of this class. And so he wrote up this demo where you can basically train a CommNet on CFAR10, the data set that we've seen before, right, with 10 classes. And what's nice about this demo is you can, it basically plots for you what each of these filters look like, what the activation maps look like. So some of the images I showed earlier were taken from this demo. And so you can go try it out, play around with it, and you know, just go through and try and get a sense for what these activation maps look like. And just one thing to note, usually, you know, the first layer activation maps are, you can interpret them, right, because they're operating directly on the input image, so you can see what these templates mean. As you get to higher level layers, it starts getting really hard, like how do you actually interpret what do these mean? So for the most part, it's just hard to interpret, so you shouldn't, you know, don't worry if you can't really make sense of what's going on, but it's still nice just to see the entire flow and what outputs are coming out. Okay, so in summary, so today we talked about how convolutional neural networks work, how they're basically stacks of these convolutional and pooling layers, followed by fully connected layers at the end. There's been a trend towards having smaller filters and deeper architectures. So we'll talk more about case studies for some of these later on. There's also been a trend towards getting rid of these pooling and fully connected layers entirely. So just keeping these, just having, you know, conv layers, very deep networks of conv layers. So again, we'll discuss all this later on. And then typical architectures again look like this. You know, as we had earlier, conv ReLU for some n number of steps, followed by a pool every once in a while. This whole thing repeated some number of times, and then followed by fully connected ReLU layers that we saw earlier, you know, one or two or just a few of these, and then a softmax at the end for your class scores. And so, you know, some typical values, you might have n up to, you know, 5 of these. You're going to have pretty deep layers of conv ReLU pool sequences, and then usually just a couple of these fully connected layers at the end. But we'll also go into some newer architectures like ResNet and GoogleNet, which challenge this and will give pretty different types of architectures. Okay, thank you, and see you guys next time.